Hi, Tatu, can you hear me?
Yes, I can.
Wonderful. Where are we at the moment with the work? Where are you?
Uh, so, so, so I haven't done physics in like 3 days, but we're starting on ideal gases.
Okay, did we start a bit? We did a bit last week.
Yes, sir.
Okay. All right. I'm not sure if Bianca is going to join. She hasn't answered the WhatsApp yet. We'll start in like a couple of minutes. Maybe what you need to do, if you have any questions, just get them together so you
Yes,
can
sir.
actually send them to me.
Yes, sir.
Do you have any questions or not yet?
No, not yet, sir.
Okay. We'll start in 2 minutes.
Yes, sir.
Um, your you must just make sure what are the chapters that you're writing on your June exam, in the June exam. I know the heading says chemical change, but that's like a huge heading. That can mean a lot of things. Can mean that you do all of the stoichiometry as well, which can be a real problem.
And did you like? She said they don't give us a scope, sir.
Not the
They don't give us a scope.
Yeah, but that's a problem.
Auntie D says we must study everything that we learn.
What I don't have your textbook in front of me. So under chemical change, if you go to the index, you can just tell me just give me all the other headings under chemical change.
Okay, so let me go get it.
Just want to make sure. So the
Hello,
textbook, what
sir.
does the textbook say?
Um,
That will be gases, probably.
chemical change, right?
Yes.
There is mole concept.
Okay.
There is molecular atomic mass,
Yeah.
molar molecular mass, and
Yeah.
molar formula mass, and the relationship between mole mass and molar mass.
Yeah.
And there's molar gas volume,
Volume.
molar mass volume.
Yeah.
Then there is Avogadro's law.
Yeah.
Then there's molar volume in balanced chemical equations.
Do you see anything that says uh, concentration?
Yes, that's the next one.
Okay, concentration, and then percentage yield, percentage purity.
Uh, I see percentage composition of compounds
Yeah.
and percentage yield.
Okay, cool. That's all I want to know.
Yes, sir.
Okay, so this is basically all your stoichiometry. That is a huge chapter that is waiting. That's the hardest chemistry chapter is waiting for you, basically. Okay, that's all I want to know. Therefore, next week we have to start with this, unless we
Yes, sir.
find enough time. Okay, right. So let's just get the gases going and finish that off today.
Yes, sir.
Okay, ideal gases. Cool. Okay. We spoke about Boyle's law,
Yes.
and we also spoke about Charles last week. Basically, what it boils down to, Boyle said that the pressure is inversely proportional to the volume,
Yes,
or you can
sir.
think about it as the volume being direct or indirectly proportional to the pressure. And Charles said that the volume of a gas is directly proportional to the temperature. Now, in Boyle's law, the temperature needs to stay constant, and in Charles's law, the pressure needs to stay constant. But anyway, this you can go and study again. We spoke about that. So I'm not going to speak about that today. I'm also not going to do the theory on ideal gases. There's a there's about a page theory in your textbook that you have to go and study. What I want to do is just do calculations today or examples. So basically, if you take Boyle's law and Charles' law and you combine it, then you get this formula here on the left.
Yes.
So this formula means that if I have a gas at a certain pressure initially, with a certain initial volume, with a certain initial temperature, and I change two of the variables. So for instance, I change the pressure and I change the temperature. Then I can just say this will be equal to the next, or the pressure in the second part of the equation, or the pressure after the change, times the volume after the change over the temperature after the change. Now, we don't need special units. You can use any unit, except your temperature here must be in Kelvin. And there's your conversion from degrees Celsius to Kelvin. So you can use any of you don't have to use SI units. Basically, you can just convert your temperature to Kelvin. So Kelvin equals your degrees Celsius plus 273.
273. Yes, sir.
Okay, you know this.
Yes, sir.
And then the other formula is called the ideal gas formula. And that you use when you have moles. Either if you have the amount of mole, or the gram, or the molar mass. If they give you the amount of moles of a gas, or the mass of the gas, or the molecular mass of the gas, then you can't use the first equation. That doesn't have any mole in it. And with this second equation in blue, this one, you have to use SI units. You have to use Pascal, you have to use cubic meters, you have to use mole, and you have to use Kelvin again. The universal gas constant is easy. That's just, I don't know why they didn't write it in here. That's 8,31. That's a constant.
Yes, sir.
All right. So the first thing we need to do is ask. If we read an example, you're going to ask yourself, are we changing something in the gas? Are we changing the temperature, the pressure, or the volume? If we're changing anything, then we use this first formula here. If they give us the amount of mole or the grams, or they ask the grams or the mole, then we use the pink formula, the ideal gas formula. That's all you need to ask yourself when you read the example. And then you just set up these two equations. So let's just play through a couple of examples.
So, sir,
Yes. Are you ready?
when I draw like, oh yes, sir.
You want this?
Should I write down the question?
Yeah, we're
the
going to do
table,
that
sir.
today. Write down the question. You can screenshot it or write it down. But first thing I want you to do is to make sure that you've got this table written down. I'm just going to write in this
Can I,
8,31. Do you have it with you somewhere?
sir, I wanna write it down.
Okay, so your pressure needs to be in Pascal. Your volume needs to be in meter cubed. And moles, obviously moles. And then your universal gas constant is 8,31. Also, you have to work in Kelvin, your temperature in Kelvin. But that's only applicable if we're using this formula. The other formula, we only have to convert the temperature to
To
Kelvin.
other units.
Yeah. So the SI units are very important for the universal, for the gas, for the ideal gas formula. And in Charles and Boyle's law, we only have to use temperature in Kelvin. You can use any other units combined with that. You can also convert to SI units if you want to, obviously.
Yes, sir.
And then tell me when you're ready.
Okay.
Ready?
No, sir, not yet, sir.
Okay, cool.
No.
So I get slightly scared if you don't have any questions, hey, Tatu. It means either good news, you understand all the work, or bad news, you haven't done a lot of work. I'm not here to check up on you. Remember, you're a homeschooler. It means you are what? Capable of pacing and managing yourself.
Yes, sir.
Good. Tell me when you're ready.
8,31.
So 1 atmosphere or 101,325 kilopascal or 101,325 pascal is standard unit for pressure. And
Yes, sir.
1 cubic meter is the same as 1,000 liter, and liter and cubic decimeter is the same. And then that's just that Kelvin conversion.
I am ready to start, sir.
Okay, let's see. Let's do number 1. The volume of, oops. The volume of a sample gas is increased from 2,5 liters to 2,8 liters, while a constant temperature is maintained. What is the final pressure of the gas under these conditions? The initial pressure was 695 pascal. Okay, now we want to ask ourselves, are they changing pressure and volume, or they're asking for mole or giving mole? They're changing pressure
said
or
it's
volume or
pressure.
temperature. So we're going to use this combination of Charles and Boyle's law, saying the pressure initially times the volume initially over the initial temperature is the pressure afterwards times the volume afterwards times the temperature, or divide by the temperature afterwards. Now, let's fill in the details. The volume of a sample of gas is increased from 2,5 liters to 2,8. So the initial volume was 2,5, and the volume is going to increase to 2,8. The temperature is constant, so temperature stays the same. That means you can actually ignore the temperature. You don't even have to have T at the bottom. It's just going to cancel. What is the final pressure? So this is what they want to know, the final pressure. If the pressure initially was 695 pascal. So this answer is going to be in pascal now, because they're giving you pressure in pascal. The temperature stays the same, so it doesn't matter what you have as T value. You can just ignore it. So I can just do 695 times 2,5, and that will equal 2,8 pressure. And then let's just calculate the work. It's really easy.
So it's 1,737.5.
Really? Did you divide by 2,8 to get P2 on its own?
Oh, no, I haven't done that, sir.
Just quickly do that also. So just divide your answer with 2,8.
620,54.
So the pressure is 620,54 pascal.
Yes, sir.
Good. Right. So the initial unit was in pascal, so my answer is also going to be pascal. I don't have to change any of the units. That was quite easy. The next one. The temperature of a 298 Kelvin. This is great. They're giving us a temperature in Kelvin. They should not have done that. Of a certain amount of CO2 gas occupies a volume of 6 liters. What will the temperature of the gas be if the volume is reduced? Okay, if the volume is reduced, the pressure will go up. Okay, now we're going to ask ourselves, are they changing volumes or pressures, or they're asking for mole or giving mole? They're changing volume. So the initial pressure times the initial volume over temperature equals the pressure later or afterwards over times the volume divided by the temperature later. Okay, let's fill in all the values. The temperature at the beginning was 298 Kelvin. Okay, and the volume at the beginning was 6 liters. Okay, we don't have the pressure. The pressure remains constant. So pressure is just going to stay P. Do you understand that?
Yes, sir.
The pressure remains constant, so I could have written this down as well. If the pressure stays the same, I can just ignore the pressure if I want to. I could have just written that formula. That's just Charles's law, basically. All right. So then P, and they want to know what will the temperature be if the volume decreases to 5,5. The temperature. Good. So I can ignore the pressure and stay the same. So it's just 6 divided.
Sir,
Yes?
so I can cancel out the pressures.
Yes, I have.
Okay.
Or you could have just used this formula right at the beginning. Can you do these examples?
Yes, sir.
Okay. So are they too easy?
Not necessarily.
Okay, cool. So let's get that value.
Okay. 6, 9, 8. So it equals to 3,66 times 10 to the power of -3.
I get 273,17 Kelvin. Let's just find some logic in it. If the
Yes,
volume decreases, the temperature,
sir.
the volume is directly proportional to the temperature. So if the volume decreases, the temperature should also decrease.
Yes.
That value you got is very low temperature. Impossible, basically. What I did, I typed in the following in my calculator. I typed in 6 divided by 298.
298.
And I got what value did you get?
0,02.
Yeah. Okay. So that was 0,0201 something. And that was
Yes, sir.
5,5 over T. So now I need to divide 5,5 with 0,0201 to get the temperature. Remember, that top one divided by that one will give me the temperature. So you made equation mistake there.
So the 5,5 I divided by the 0, comma.
Or you can just say, look, I'm just gonna some kids just cross multiply. In other words, they do this. They multiply cross. Then you have 6t equals 5,5 times 298. And then I just divide the 6 underneath that answer. Do you understand what I've done? Because I've got one fraction on the left and one fraction on the other side, I can just cross multiply. See if you get 273,17.
T equals 98. Okay, let me just do this. Clarify. Equal to 9 divided by 6. I get 273,16667.
Yeah, so it's 17 Kelvin.
So can I write comma 2?
No, 2 decimals is 17.
Okay.
Maybe just take a screenshot of that.
Okay.
Can you remember how to do a screenshot or a snippet or whatever?
Yes, sir. Let me just do
Good.
it.
Tell me when you're finished.
Yes, sir.
Right. A cylinder of propane gas is at a temperature of 20 degrees Celsius. So, exclamation mark, temperature can't be in degrees Celsius. And the pressure is 8 atmospheres. When a cylinder has been placed in sunlight, its temperature increases. So the temperature later on is 25 degrees Celsius. What will the pressure be?
Okay, so a cylinder of propane gas at a temperature of 20 degrees exerts a pressure of 8.
Okay, now,
When
okay. So at the beginning, is this a beginning end sum or a mole sum? It's a beginning end sum.
yes, it's a beginning answer.
Very good. So
And we gotta
P1
convert.
V1 over T1 equals P2 V2 over T2. Is that correct?
Yes, sir.
Good. But now they've got something in here that's quite interesting. They've got a cylinder of propane gas. There's my cylinder.
Yes, sir.
So that cylinder, the volume is stays constant. Remember, it's a metal cylinder. It can't
Yes, sir.
change in size. So
Yes, it can't
basically what
change.
we can do is just ignore the volumes, because the volume of the cylinder is not going to change.
Yes, sir.
Right, good. So let's say the pressure at the beginning is 8 atmospheres and the temperature is 20 plus 273, because I have to convert that temperature to Kelvin. And Kelvin equals the degrees of Celsius plus 273. So I'm just going to put that in the equation. I'm not even going to work it out separately. And that's over the new pressure. I don't know what it is. And the new temperature is 25 plus 273. So I'm just going to solve that equation. I want to see if you can solve that equation. It's important that you are able to solve equations.
Yes, sir. Okay, at first I'm gonna be like 8 divided by
Yes.
293.
8 divided by
sir?
what? This in brackets? No?
Yes,
Or
sir.
you're going to put it
Yes.
on a fraction sign?
Yes, and it's gonna give you 0,027. So 0,3. Can I
Yes.
write it like that? 0,3.
And then you
is
multiply
equal-
that with this part in a fraction, in a bracket. No.
Yes, sir.
The pressure should be higher because the temperature gone up. So the pressure needs to be higher than 8. Slightly higher. The temperature went up slightly with 5 degrees. So the pressure should go up slightly. I get 8
I get 8,14.
atmospheres. Very
Yes, sir.
good. Very good. Very good.
But that's
Good.
what the ATM stands for, atmosphere.
Atmospheres. Yeah, that's atmosphere is the same, is also a standard unit. You can let's just go back to that. I'll come
Yes,
back to
sir.
this example. Just check here. You can either have 1 atmosphere as a standard unit, or you can have 760 millimeters of, what's that called?
Hydrogen.
Hg. This is mercury.
Oh, mercury. Is it mercury Mg, sir?
No, magnesium is Mg. Mercury is Hg. This
Oh.
comes from the following way of measuring it. You get a tube, and then they put a thin, okay, it's a double-sided tube. I can't really draw that, but anyway, what happens is they fill it with mercury. It's a metal, but it's a liquid.
Yes,
So if
sir.
the temperature goes up, then the mercury goes up. So basically, the measurement between this part at sea level or at 1 atmosphere, the mercury will rise up to 760 millimeters.
So, sir,
Yes.
mercury is the same thing that they use in like thermometer, right?
Yes. And yeah, in a thermometer, it's that shiny metal line.
Okay.
So it's a mercury line. Okay, cool. So you've got various ways of referring to standard pressure or SI units. You can use mercury, 760 millimeters mercury, 1 atmosphere, or 101,325 Pascal, or 101,325 kilopascal. Good. Let's go back to the example. Did you screenshot this example?
I drew it down, yes, sir.
Okay, do it.
Yes, sir. Screenshot.
Right, we've got 3 examples left. Then we're going over the stoichiometry.
Okay,
Boom.
sir.
Example of gas exerts a pressure of 100 kilopascal at 15 degrees Celsius. The volume under these conditions is 10 cubic decimeters. The pressure is increased to 130 and the temperature increases to 32. What will the new volume be? Okay, now we've got all the variables. So pressure at the beginning times volume at the beginning over temperature at the beginning equals the pressure later or afterwards times the volume afterwards over the temperature afterwards. And now we have to convert all the units. I'm going to give you 3 minutes to complete this sum on your own. See if you can do it.
Please don't start the thing. I just want to draw down my units on the thing first.
No, you only have to remember this is a before after sum. So only the temperature needs to be in Kelvin.
Yes, sir. Okay.
Only when you're going to be using the PV equals nRT, then we have to use all the standard units. Because the constant is the R is valued, the R value is at those specific constants.
So, sir, the pressure, I don't have to convert it.
Pressure doesn't need to be converted. You can. It's not a problem. If you convert all to SI units, you'll get an answer in SI units.
Oh, okay.
You can convert everything, but it's not necessary.
Okay. Equals. Then B1 equals 2 B2 plus 273, right? Then this is equal to
You happy?
no, sir, not yet, please, sir. I'm still finishing.
Do you need help or you're fine?
I'm fine, sir.
Okay, wonderful.
So my final answer is 8,15.
Okay, 8,15 what?
Volume, right? Meters cube.
Is it decimeter cubed?
Decimeter.
Well, I'm
Okay,
just
so
stealing that unit that they're using from the beginning. Okay, let's see.
yes.
Pressure at the beginning is 100 kilopascal. The volume at the beginning is 10 cubic decimeters. The temperature is 15 plus 273.
Yes.
So the pressure at the end, it increases to 130. If the pressure increases, the volume should decrease. Yes, very good.
Yes.
I can see your answer is going to be right. So what's the volume? The temperature is 32 plus 273. Okay, now the temperature is increased, so that will make the volume even now bigger. So that's just a problem. We don't know what's going to happen here. Okay, so I'm just going to type in the left-hand side of my calculator. So what they do, they just type in that left on the calculator. So that's 1,000 on top with 15 plus 273. And that gives me
It equals
3,47 and then a couple of twos. Now,
yes, sir.
now there's various ways of doing. Some students just type this in their calculator and write it next to V2. Or you can do it in one go if you want to. So this becomes 0,42622 V2. And then you just divide the left with the right. So it's 3.47 with a couple of 2's divided by the answer I just got. And that's 8,15. Excellent. The volume is 8,15.
I'm right.
Yes. Why would you be sound amazed? You're all right. Good.
I'm right, sir.
Okay, two sums. We're going to look at the mole. Carbon dioxide gas is produced. Did you take this sum? Did you take a screenshot, yeah? Or did you wrote it down? But just take a screenshot as well, so you can get all your stuff in one area. You can make a little folder with all this in.
Yes, sir.
Great.
I just took it now.
Carbon dioxide is a gas produced as a result of reaction between calcium carbonate and hydrochloric acid. The gas that is produced collects a container of unknown volume. The pressure of the gas, okay, let's go. The pressure is 105 kilopascal. And the temperature is 20 degrees Celsius. If the number of moles, yes. Can you hear me?
The screen that you're sharing it's small, yes, sir, but the screen that you're sharing is small. I can't see the question. I don't know, it just became small. I don't know.
Okay, let's just your screen, new share. Now? Is it the same?
Still the same, sir.
But that's, yes, sir. I think it might be a problem on your side. I'm going to try and re-share the screen. Did you play with the refresh rate of your PC?
Sir?
Can you see it better now?
No, sir, it's still small.
That's interesting. Now?
It's still small.
But is it full screen on your computer?
Okay, yeah, now it is, sir.
Okay, good. Right, let's read again. Carbon dioxide is a gas, and it's produced by taking calcium carbonate and just putting it into hydrochloric acid. The gas is collected in a container with an unknown volume. So we don't need the volume. We don't know the volume. The pressure of the gas is 105 kilopascals and the temperature is 20 degrees Celsius. If the number of moles of gas that's collected is 0.86, aha, what is the volume? So now I'm using this formula. PV equals nRT. And now my temperature needs to be in Kelvin. So it's 20 plus 273. And that's I'm just gonna put it down here as 293 Kelvin. My volume, I don't know. The pressure needs to be in Pascal. We can't use kilopascal, but that's just multiply by 1,000 to get it to Pascal. That's 105,000 Pascal. And we need, mole is a standard unit, so mole is fine. I want to know what the volume is. So PV equals nRT. So I have 105,000 times the volume equals N, which is 0.86, times that gas. I'm just going to put this to the side because I don't have enough space. R is 8.31 and the temperature is 293 Kelvin. So this is easy. I'm going to type the right-hand side of my equation into my calculator and just divide it by 105,000. So then the volume is 0.0199. So it's 0.02 cubic meters. That's the standard unit for volume. Well, my screen is jumping around. Maybe that's why. What do you see now?
I'm still writing this thing down. Okay.
Bigger now the screen.
Yes, sir. It's full.
Okay, full screen.
Okay. Then I divide it by. So my answer is 0.86. comma, yes, so it's the same.
Excellent. Okay, let's make it full screen, and then you can take a screenshot.
Sir,
Yes.
do you have worksheets in which you can send to me on the group so that I can practice with?
I don't
Because
have on Boas law. Look, it's something that a lot of schools is skipping because you're not going to get examined on it in grade 12. So a lot of schools are just skipping this chapter because you're not, and then they're not asking it in the grade 11 syllabus because they know you're not going to be examined on it in grade 12. So they're cheating. I don't have, I'll try and find, but I don't have a lot of English worksheets on gases, but I have a lot of stoichiometry worksheets. Right, next example. We have calculate the mass. What is the mass? What is the mass of nitrogen gas? If you needed to inflate a sample of an airbag, if the volume you need to inflate is 65 decimeter cubed, that is a problem. And the temperature is 25 degrees Celsius. And the pressure is 99.3 kilopascal. Assume the gas temperature remains constant during reaction. Okay, that's fine. Okay, so this is a PV equals nRT sum because I want to know the mass, and mass is related to moles or mole, depending on which English country you live. Right, now I need to convert that pressure to Pascal. So I need to multiply that with 1,000. So the pressure is going to be 99.3 times 1,000. What's that? You just move the decimal 3. So that's 99300 Pascal.
yes, sir.
99300 Pascal. The volume must be in meter cubed. So the volume, which is 65 decimeter cubed, must be converted to meter cubed. Now, a decimeter is like 10 centimeters. So decimeter conversion to meter is divided by 10 because there's 10 decimals in a meter or decimeters in a meter. So decimeter cubed to meter cubed is divided with
6.5.
Yes, very good. 65 divided by 1,000 is 6.5 to the power of 0.065. No, well, you can have 6.5 times 10 to the power of minus 2. Which one do you have?
So I'm dividing by 1,000 or
You divide by 1,000, yeah.
okay. And my final answer is 0.065.
Yes. Now the mole, I don't know. And the R value is 8.31. And the temperature is what? The temperature is 25 plus 273 because I have to convert the temperature to Kelvin.
Yes.
I'm just going to take these conversions away. Right, so let's work out those mole. See if you can get, if you get the same value, 2.606 mole. I'm going to recalculate it. Yeah.
The answer is 2.61.
Yeah, I'm gonna use 4 decimals. The reason is this is not the question. And if I round off too quickly here, I'm gonna mess up the answer. The question is mass. So mole equals mass over molar mass. So the mass equals the amount of mole, which is 2, let me just try and write that neatly, 2,6064 times the molar mass of nitrogen gas, which is diatomic. So it's 14 times 2. The molar mass of nitrogen is 14. So I'm just going to multiply my answer with 28. And then I get 72,98 grams. Now, if I round it off too early in this top part here, then I would not have got that answer exact. Then I might have lose some marks because I rounded off somewhere in the middle of the sum, where I should not have rounded off there. If I round off there, I don't get an accurate answer.
Yes, can I just take a screenshot?
Okay. Let me just get all of us in before you take that screen.
Yes, like, got it.
Good. Okay, we're going to talk about, we finished with this chapter. Just want to see if there's anything I don't have any worksheets on this gases. Not in English. No. No. But it's not difficult to find, eh? You can download past papers and you'll find it there. Right. We're just going to talk about stoichiometry. And then we're going to do one thing, and then we're finished. And then we're leaving all the grade 11 work for next week. So we're just doing some slight revision on grade 10 stuff, empirical formula, and then we do leaving the grade 11 work for next week. Okay, so this.
Can I write this down?
Yeah, you can. I'm going to discuss this flow diagram with you.
Yes, sir.
But not today. So I will give you this flow. This is a very important diagram. It's going to show you how to basically do your stoichiometry, which is mole sums. Yeah. Okay, let's just do empirical formula. Can you remember this? You did this in grade 10.
Sir.
Empirical formula is basically the most, how can I say, if you write something, if you write a molecular form, if you write something in its molecular form, empirical formula is basically the most, how can I say, just hold a second. Sorry, Tatu. I just had to mute myself.
Yes, sir.
So empirical formula is the most, how can I say, I don't know how to say this in English, but if I have C8H12, that's a molecular form. Empirical form is I can divide the 8 with 2 and I can divide the 12 with 2. Then I get C4H6. But then I can divide both of them with 2 again. I get C2H3. So that's my most basic ratio in which carbon and hydrogen can bond. But it doesn't give me an indication what the molecule looks like. It's just the most basic ratio in which those atoms can bond. That's what we're going to work out. Okay, so we have chlorofluorocarbons. It's a class of compound that is a long history, blah, blah, blah. CFCs are slowly being passed. Okay, they're giving you a lot of lecture now. So Jabu has a sample of CFCs that has the following percentage composition. We have 14,05% carbon. we have 41,48% chlorine, and we have 44,46% fluorine. Now, they want you to determine the molecular formula if it has a molecular mass of 171 grams per mole. So the first thing we're going to do, we're going to determine the empirical formula first. So we're going to work from the empirical formula to the molecular formula. I'll show you how to do that. Now, the empirical formula you did last year, basically they taught you how to do it last year. So now, very important, if we're working from percentage to empirical formula, you choose what? Can you remember? You choose 100 grams. Why? If I choose 100 gram as my sample, then 14,05% of 100 grams is just 14,05 grams. And 41,48% is just 41,48 grams. So by choosing 100 gram, I can choose any value. If something is bound in a certain ratio, like Coca-Cola, if you have Coke and 70% sugar and 30% water, then it doesn't matter how much Coke you put in a glass, it will have that same ratio of 70% sugar. So I'm going to convert, I'm going to choose, so we're going to choose 100 gram, and therefore my carbon is going to be 14,05 gram, and my chlorine is going to be 41,48 grams, and my fluorine is going to be 44,46 grams. And that means the following. I can work out the mole of each of them. I can work out the carbon, the chlorine, and the fluorine amount of mole in each of one of those. Because the mole is the mass divided by the molar mass. Mole is mass divided by molar mass. Mole is mass divided by molar mass. Okay, let's start. Carbon. We have 14,05 grams, and that divided by 12, because the molar mass of carbon is 12. Let's put that in a calculator. And that gives me 1,1708. 1,1708 mole. I do the same with the chlorine. The mass is 41,48, and I divide it with 35,5. I think, do you have a periodic table with you?
Sir?
Chlorine is 35,5, isn't it?
Chlorine, yes, sir.
Okay, let's just do that calculation. 41.48 divided by 35.5. It's 1,68. So it's, 1,168. So it's basically the same. They're both 1,17 if you round it off to 2 decimals. And then fluorine, the amount of moles is 44,46, and fluorine's molar mass is 19, I think. Just check on your periodic table.
Huh?
Is it fluorine 19?
Yeah, fluorine is 19.
Yes, good. So 44.46 divided by 19. And that is 2,34. So now I have each one of those mole values. So the carbon to the chlorine to the fluorine is 1,17 to 1,17 to 2,34. And I divide everything with the lowest value. Then I get 1 to 1 to 2. So my empirical formula, just going to zoom out a bit. My empirical formula is C1, Cl1, F2. Carbon 1, chlorine 1, fluorine 2. Do you understand that?
Yes, sir.
Okay, but that's my empirical formula. Now, they want to know what is the molecular formula. So the molecular formula, if the molecular mass is 171 grams per mole, So how do I do that? I'm going to determine the molecular mass of that empirical formula. So the CClF has 1 carbon, 1 chlorine, and 2 fluorines. That was 19 times 2.
19.
Right, let's do that. 12 plus 35.5 plus
37. 47.5. I'm like the answer.
no, I get
Podcast.
85.5. 12 plus 35 plus 19 times 2.
Yes, it is.
Is it 85.5?
Yeah.
Okay. Now I want to find out how many times can 171 be divided by 85.5?
Twice.
Yes, twice. Therefore, I have to double up each one of those. So the carbon needs to double. So I've got C2. The chlorine needs to double. I've got Cl2. And the fluorine needs to double. I got F4. And there's my molecular formula. Now, this is you're not going to fit into one page. So let's see what we can do. I don't know how you're going to photograph this. Okay. If something's gone wrong with the photo, you can always go online on the website and just forward the video until you get the screen again and just write it off.
Yes, sir.
Okay, so this is basically what you must be able to do with regards to empirical formula in grade 11. There's also a couple of more examples and your textbook will have them in. I'm expecting next week more questions.
Yes, sir.
And then all I'm going to do now is just show you what we're doing from now on. So I'm just going to do my own example. Let's assume that we have magnesium solid and we have 80 grams. And we're going to burn that with oxygen gas. And that's going to be in excess. Excess means there's no shortage of oxygen gas. And that will give me magnesium oxide, which is a solid. And I'm balancing the equation. I'm putting a 2 there in front so that I have 2 oxygens on the right-hand side of the formula. And therefore, I have to have 2 magnesiums on the side. So now they're going to ask you, how many grams of magnesium oxide do we produce if we're burning 80 grams of magnesium into excess oxygen? Okay. So I'm going to follow that flow diagram. The flow diagram looks like this. I'll show you this. You start off with either a mass of a reactant or with its concentration or with its volume. Now, in this case, we have the mass. We have 80 grams. And then we're going to work out the mole of my reactants. So the first step is going to be, we're going to work out how many moles of magnesium do we have. Then we're going to do a mole ratio between the reactants and the products. And then we're going to answer the question. The question is either going to be how many grams or what the concentration or what the volume of the product is. In this case, they ask the mass again. So I'm just going to delete this and take this little flow diagram to our sum, and then we're going to do it there. This flow diagram is going to solve a lot of questions for you. Right, here we go. Just going to make it small so we all can use it. Right, so let's start with the flow diagram. The first step is going to be to determine the amount of mole of the reactant, magnesium. So I'm going to start with magnesium. And the mole is the mass divided by the molar mass. So in this flow diagram, you get all the equations as well. So the mole is 80 grams divided by the molar mass of magnesium, which I think is 24.
Yes, sir.
80 divided by 24. And that gives me 3,333 mole. Now, I'm writing that down, but I'm keeping that long decimal answer in my calculator. Now I'm going to look at the ratio between my reactant and my product. And they have a 2:2 ratio or a 1:1 ratio. And that means the next step, which is my ratio step, I know that the same amount of mole of magnesium oxide is formed. Why? Because for every 2 moles of magnesium, I get 2 moles of magnesium oxide. Or 2 units of magnesium gives 2 units of magnesium oxide. So I can immediately say that the mole value of the magnesium oxide is also 3,333. And I'm making a little note here for the person marking my test that they can see that I knew it was in a 1:1 ratio. And then I answered the question. So we did this. We worked out the mole of the reactant. We did a ratio. We worked out the mole of the products. We have the mole of the products. And now we're going to work out the mass of the product. And the mole is the mass divided by the molar mass. So the mass is moles times molar mass. We have 3,333. And the magnesium oxide is just 24 plus 1 oxygen, which is 16. So I'm going to multiply that answer I've got in my calculator with a bracket 24 plus 16 and then close the bracket. And then I get 133,33. 133,33 grams. Okay, this is also sort of last year's work. This was also some schools did this last year. We're almost finished. Just make a note of that or write it down or take a screenshot.
Yes, sir.
And tell me when you're ready.
Yes, sometime.
Okay, now I'm just going to show you what we're doing this year. We're adding on. So I'm just going to take this away. We're not going to calculate this. Oh, can't take everything away. So this year, I'm not going to tell you the oxygen is in axis. You have to find out which one is in axis. So we're going to do a limiting reactants. We're going to find out which one is in axis and which one is limiting the reaction. So therefore, I could have given you 80 grams of magnesium and not say that oxygen is in axis, but say, I've got 100 grams of oxygen. And then you have to work out which one of them do I have in axis and which one will in the reaction be used up first. And that's called limiting reagents. And we're going to do that next week. Then you use the limiting one to determine the product. You can't use anyone. I can't just choose the magnesium to work at the magnesium oxide. I first have to work at which one is stopping the reaction first. Because you would agree, if I have a container here, and there's a piece of magnesium in there, and oxygen gas, if I light that up and it starts burning, if the oxygen finishes first, then the reaction will stop because it will stop burning. But if the magnesium is finished first, then the reaction will also stop, but then there will be a certain amount of oxygen left. And we have to determine how much oxygen is used, how much is left, if the oxygen is in excess or if the magnesium is in excess. And that we'll do next week. Okay. There is not enough time to start with that. So all I can tell you is finish that gases, the worksheets in your book as soon as possible, and then you start with stoichiometry, the empirical formula sums, and also limiting reagents. Don't do percentage yield and percentage purity before you do limiting reactants. Okay. Do you understand?
Yes, I do.
Okay, I'll see you next week, or I'll see you when we've got maths.
Yeah.
Keep well.
Bye.